speak a little bit about another procedure, and this procedure here is applied in context of non-stationary financial time series. But actually we have some more applications of this procedure, and I hope you will see in the afternoon some further examples how this procedure can be applied. And so this is one of the most powerful procedures, and the idea behind I will explain in a moment why we are not so much happy with the local model selection and why we draw this local change point. But first I show a couple of motivating examples. So what you see here is the stock price of Allianz, and this is the corresponding daily returns for the time interval, which I cannot see here, from the beginning of 74 to something middle of 94, so more or less 20 years. And you see here clear type inhomogeneity. You have the period of small volatility or huge volatility, and this alternate and so on. So you cannot model this by Black-Scholes. So you cannot assume constant volatility here. Okay, so but you need to estimate volatility, and you need to estimate volatility from the historical data. This is a usual practical problem. So this is the model. ST is the asset price, YT is the log returns. In our regression-like setup means that the returns given the past is distributed from some simple parametric family, which depends on the parameter f of xt, and this parameter is exactly volatility. So basically, if you know the volatility, you know the distribution of the t return given the past. And this is what you need, because you need to do your value at risk or portfolio optimization. You have to do it on the basis of historical data, but you don't, and for this you of course need to know the distribution of YT. And this f is a function of xt. Xt could be just time, but it could be some other endogenous variable, or even endogenous, so I mean something which is observed on the market or probably not observed on the market. So we stick today to the following conditional heteroscedasticity model when the returns are here. This family is a volatility family. This means that there's a normal distribution with zero mean and the variance f of xt. So this is written here. Yt, the return, can be decomposed as a volatility parameter sigma t times epsilon t. Epsilon t is an innovation which is given the past standard normal, and sigma t is a volatility which depends on the past and just unknown value, which actually you want to recover. And your problem is to recover sigma t given the preceding observations. This is a problem, typical problem in financial engineering. And now how you can attack this problem? Again, we know, just find a good parametric model. So parametric specification means that the function is coded by finite dimensional parameter vector theta. And so the simplest model would be that the f is just theta. But we will see some example right now. And this is the first example. F theta is equal to theta. This is a famous Black-Scholes model. Volatility is just constant. Theta is a parameter. And you want to recover this. So if you are not happy with Black-Scholes, and this has good reasons, you can think about other parametric specification. This is arch of angle. You take the squared returns, p squared returns from the past, intercept omega, coefficients alpha 1 to alpha p, and you say your volatility is linear combination of the squared returns in the past. This RHP model, so you know from practical experience to model well the real data you need this p about 10, 12, etc. This is not feasible. And the alternative was suggested Bolerslev, you take the Garch model such that you include in this model also the previous volatility value. This already non-linear time series modeling, and you have 3 parameters for Garch 1, and this is already a good model for future volatility. Rather good. So you have just 3 parameters, and this is a feasible model to apply for financial engineering. Okay, but still we will see some problems. So what you see here is the realization from Blake-Scholes. I don't know what it has to do here. So now, if the model is correct, we know what to do. This is exactly our starting point. In the parametric situation, if the model is given, then you know the joint distribution of the returns, y. And this joint distribution is described as a log likelihood, which is sum of log likelihood of individual observations. This formula continues to apply in time series context because we consider conditional distributions. So if we have this log likelihood, we define the estimate by maximizing. You can write maximize estimating equation. There is a whole machinery how to compute this estimate. And okay, this is a parametric theory, and this parametric theory can be again put in this one line. If the parametric model is true, then the fitted likelihood, which is written here, minus likelihood at the true value, this difference is stochastically bounded with moments. This is exactly the same result as in a general parametric framework. This result requires some condition which I don't mention here, but for instance for Garch model it applies without any problem, provided that the coefficients are within the ergodicity. So, okay, now the specification for Blake-Scholes. Then you here have the constant volatility. In the parametric situation, you go back to the volatility model. Everything is known already here. You have the explicit form of the estimate. Estimate is the sum of squared, y is the squared returns, and the estimated volatility is the mean value of the squared returns, and the quality is measured by this fitted log likelihood. And the result says basically that the quality of estimation is of order n to the minus 1 half. Now we can apply the same to the Garch model, and again you have 3 parameters. Here you can write the corresponding log likelihood. Now it is a little bit more complicated because everything depends on this parameter vector theta. Theta is omega alpha beta, but in the special nonlinear way. If you fix omega alpha beta, then you can define the volatility process, and it should be plugged in the likelihood. And then you optimize this expression with respect to theta. It's already, there is no explicit solution. It should be done numerically and with care. Actually, it's not a big issue to solve this problem, this kind of optimization problem, just to find the estimate. Even in the parametric situation, it's not so easy. But now I want to discuss a little bit advantages in the problem with parametric models. So still, in this Garch model, there are well-developed algorithms. There is some asymptotic theory. So practical experience shows that the Garch model is very good in sample. And Garch model can reproduce the most of the stylized effects of the financial time series, like volatility cluster. But there are some drawbacks of the gauge modeling. And so actually the confidence intervals for gauge model are quite high, especially for beta. And you need a huge data samples to carefully estimate the parameters. And the most important is our general point. Everything works well if the gauge model is a true one. You assume the data are from the gauge model. If they come from the gauge model, then you have more or less reasonable quality of estimation. But if the real life is not gauge, what happens? This is the question. And this is one small illustration what happens in the real life. Could happen in the real life. It's a simulated example. So what you see here, this is simulation from change point gauge. So what means change point? You have three parameters, omega, alpha, beta. Parameter alpha and parameter beta are constant. Unfortunately, this is cutted, this plot. But the parameter alpha and beta are constant over the time. And only parameter omega jumps at this point from value of 0.25 to value close to 1. Only parameter omega. Now we estimate at every point all the parameters, the gauge parameter from the historical data, from the left. And this is what you see here. The black points are the median of the estimate, and you see the quantiles, blue is 2575 quantiles, and green are 595 quantiles. So what is happening before the jump? We have a really gauge model. And you see here, for the parameter alpha, we have relatively good confidence intervals. For parameter alpha, you have much larger confidence interval, and for parameter beta, even larger. But still, it's more or less homogeneous. Now, you have the region here. You estimate from this data, from 500 points, you estimate, and this 500 points includes the jump in the model. The gauge model is not true anymore, because in the data generating process, you have a jump at this point. The model has been changed here, but your procedure does not know estimate as it would be gauge. And what you see here, estimated parameter jump here, the true parameter jumps to 1, estimated parameter jumps to 0. Here, estimated parameter for alpha jumps also towards 0, but the parameter beta jumps to 1. And this means you switch from normal regime to high pass filtering. You have here low pass filtering with a relatively small beta, and if the regime here is changed, then your model automatically jumps to another regime, which means actually high pass filtering. Instead of learning, the gauge model automatically switches to the situations that you just take very few amount of data.
Is this a realistic jump?
Of course, it's exactly what is observed in the market. Typically, parameter omega jumps. So you have just changes the price and changes the volatility by some constant. This is exactly what happens in the market.
Yeah, sure, I believe that if omega jumps, but the question is whether the size of the jump is realistic.
It's small jump. Typically, it's much larger.
Excuse me?
Typically, the size of the jump is much larger.
Then this indicates that the gauge one is probably not the right model anymore. Then we have some jump. You need some jump component.
No,
This is really a huge jump.
No, not really. So what I would like to say, you have to be careful with gauge model. This is because if there is non-stationarity in the data, this gauge model can be completely misspecified. And there is a well-known effect, integrated gauge effect. alpha plus beta close to 1. And so another explanation is the real life is non-stationary. You automatically go in this regime with big beta because of non-stationarity. This is what we observe here. Okay. So and there is some more evidence here, some of the reference where the people confirm the same phenomena. Okay, so now what we try to do, we apply our local parametric approach. Then if you like gauge, it's your choice, you can apply gauge, but now we want to do it systematically and adaptively. This means we combine this gauge modeling with a check of the parametric assumption. So what we say here, so non-parametric modeling, you have just volatility, Ft. Parametric assumption means local parametric assumption. In the interval capital I, you can approximate the function by some parametric specification. And then, so if the interval is given, everything is clear. You do estimation from this interval. You only use the data from this interval of time homogeneity. That's all. This is the whole extension. The only question is how to select this interval. And now we more or less know the idea how to do this. We select the largest interval where the parametric assumption is not significantly violated. In this, the measure of significance is the modeling bias, and we have the formula for the modeling bias. We take the Humboldt-Labrador for two normal distributions, one with a true parameter Ft and the other with an approximating parameter F theta. And small modeling bias condition means that this guy is sufficiently small. But the small modification here, small difference to the previous situation is that now this F theta and Ft both are stochastic. It's predictable processes here, and therefore this value is stochastic. Therefore we say small modeling bias condition means that this guy is small with high probability. Okay, now type 2 result, extension from parametric to non-parametric under SMD. We see what happens if the interval is selected correctly. This means that expected value of this modeling bias is bounded by capital delta. Earlier we have just this guy bounded by capital delta, now this is random, and our small modeling bias condition means expected value of this guy is bounded by capital delta. So this is a condition which says this interval is a good interval. And we want to mimic the largest good interval. This is what we want to get. And the theorem says if we have this condition, then we have the same type of results. The risk of the parametric estimate, the loss normalized by risk is bounded by delta plus 1. So we have the same type of the result. So here we have loss of the parametric estimate divided by the risk in the parametric situation, and look what happens in the real situation, and this is bounded by delta plus 1. This is the same type 2 result as before. Okay, now we want to present a procedure which is called local change point, and this procedure exactly realizes the idea which we would like to have. We want to select the largest interval of time homogeneity.
And why don't we use Lomos LMS here?
You don't use it. Who don't use it?
We cannot use LMS here.
You saw this.
No,
You like them show?
for this situation.
Of course. You saw this, exactly.
Yeah, okay, that's true. I saw that, yes, but not for gauge.
Not for gauge, of course you can apply. I just want to say a few words why a local change point, and it is written here. So the idea is they select the largest interval of homogeneity by testing the parametric hypothesis. This idea is exactly as before, as for local model selection. But now we do another way of testing, which test against a change point alternative, and you can ask why against change point. Why you do such kind of test, and here there are good reasons for this. that this change point test delivers much more information. It not only says there is change or not, but it only says when this change occurs, and so it gives some indication of the change. And additionally, it is much more sensitive to local model selection, because you have much larger class of alternatives. Local model selection looks only one direction, just compared to different estimates. Here you made the check for all internal points. So in this sense, you should be more sensitive with this procedure. Okay, so the setup is more or less the same. Now I explain a few words what this change point test means. So you have your null hypothesis that the function is parametric within the interval capital I. This is your belief. And this belief you want to check. So it could be Garch here, or Arch. So first you write your log likelihood under the null hypothesis. This is the case that Ft is exactly f theta. Now you consider the alternative, or more precisely change point alternative. And this means that there are two different parameter vectors, exactly as we saw in the example. So this is a theta, both theta is a parameter vector, theta 1 and theta 2. And what happens, this interval is split into the two subintervals, j and j complement. And you have one model for j and another model for j complement with different parameter values. So this is two different vectors. Okay? Then the corresponding joint distribution can be split also into two parts. You see here for j you have the parameter, the process described by parameter vector theta 1, and here you have the process described by the parameter vector theta 2. Okay? So and now what is the test? This test is a so-called likelihood ratio test. It looks like here. You maximize under the alternative for the couple of vectors theta 1, theta 2. This is a fitted log likelihood under the alternative. This is a fitted log likelihood under the null hypothesis, and you look the difference. If the difference is significant, then we say the change point is detected. This means that change point alternative fits the data much better than the constant parametric specification.
And the M is chosen by me. So on the previous slide, so the interval, the length of the interval, so this t.
No, it's for given interval. For given interval, later we will do it for every interval. We'll have a sequence of intervals.
The minimal n is again 20.
Exactly.
Okay,
You start with 20 and then you increase it.
Okay.
But this is only a testing procedure.
Yeah, for one n.
So you see here you have the tested.
Test against
One thing I should say additionally, so this is for given split with a point tau, and what we do additionally, we maximize over all possible splits. If you go back, you see here this is a split point tau, and this tau is taken differently. And so we maximize within the set of internal points. And we say the change point is detected if this maximum is over the critical value. This is a classical change point, and it's not our discovery, and you can find this in the literature. The only question is how to select the critical values. Okay, so now the procedure. So what you do, you fix first the set of nested intervals, exactly as Mrs. Love presented before. Okay? You have the sequence of intervals of the length mk, and you want to select the largest interval which is not projected. Okay. Now the procedure is as follows. You start from the smallest interval, you check it on the change point, and if you have change point, then you go to the previous interval. Otherwise you accept. And finally you select the latest non-rejected interval. So basically the same kind of the procedure, the only difference is that you have another test. Earlier it was a test of homogeneity by comparing different interval confidence set, and here you check by this change point analysis. Okay, this we don't need. Now again about the parameters. So you need to fix the set of intervals, this exactly as before, nothing new. Additionally, you have to fix the set of interior points. And this is one proposal among others, that we check every point is a candidate on the change point, but only once, actually, in the time. So this is probably, I can do some illustration here. What happens? This is, I guess it is missing here. Yes, that this is a story like it. Also, you have first interval and the set of it is accepted all the time. That is the second. So this is P1. Then you have I2 and so on. I3, and each time you check all these points as candidates of change point. So this is a candidate of change point for interval I. This is tau, this is j, and this is j complement. And if you go further, then again you take this interval, which is shown exactly here. The set of candidate change point is a difference between the interval k minus 1 and the interval k minus 2. And this automatically provides that your every time point in the history is only once a candidate for the change. Okay, now the critical value are selected again by this propagation condition. So you have the parametric risk bound I mentioned. And what we check is that the difference between the oracle estimate for the interval ik coincide this and the adaptive estimate for the k step. This difference is not large enough. So you provide again the first kind error probability. This is the same condition as before. So you require that your procedure works as you would like to work in the parametric situation. You look how it works. So if you work with GARCH, if GARCH is your favorite model, you model many times from GARCH and provide that it works well in the GARCH situation. You don't reject the true model very often. This is usual in hypothesis testing. You just apply another loss here for measuring the first kind error probability. Good, you have the same bound for the critical values. It's logarithmic in the sample size or linear in the number of intervals. It's the same. And again, you have this shape that the critical values are larger at the beginning and goes down. With the same interpretation. At the beginning, you should be more conservative as at the end, because you pay more for false alarm. Good. Now we know. So this is the same kind of theory which you can derive for this local change point procedure. So you have oracle choice. You have the propagation property, which is automatic in the sense that this property is provided, this ratio is bounded by definition, by construction in the parametric situation, and can be extended to the non-parametric situation under SMB with this payment capital delta. And you have the oracle result, which is actually the result which says that there is a bound between the oracle choice in the final choice. So basically this means that the final estimate belongs to the confidence interval of the oracle estimate. So the theory can be extended here as well. There is no big difference. This oracle result, or stability result here, which is shown inside of here, says that this is also a good procedure. It also provides, this change point test also provides kind of stability result. Good. Now everything can be done. So here is illustrated for local constant volatility modeling, and this is what Mstislav will show in a minute how it works. For LCP, I just briefly summarize. So in this case, the volatility, so the function f is constant, is a good estimate from the interval n. I is a mean value of the squared returns. Y is squared returns. And fitted likelihood can be written as n times Kuhlberg. And therefore, there is a very compact representation for the test statistic. So you remember, is a likelihood ratio test statistic, and here it can be computed by two arithmetic operations. So you have three estimates, one for the interval, one I, this is the estimate for interval j, and this is estimate for interval j complement. Each three estimates are mean values, and you compute this Kuhlberg for normal formula, and this is a test statistic. And you maximize this over tau. Tau is a splitting point. So this is really easy to implement. And maybe this is only a numerical example which is very old, and I suggest instead of showing this example, Mstislav show how it works.
So here we have a demo program very similar to that shown before. The main difference here is the one that reflects the difference between the two methods, namely the middle window. In this window, instead of the weak estimates with the corresponding confidence intervals, we have the critical values that are denoted as red points, and test statistics corresponding to the same interval to which the critical value corresponds. As before, the horizontal position of the red points, of the critical values, shows the length of the interval, and they all have common right edge at this point.
Maybe I just comment here once again what we have here, these black lines. So for every interval of length of this length, we computed the change point test statistic, which is was denoted by Ti. So this length is the value of the test statistic Ti. For the interval, or Tik, Ik is the current interval, this is a test statistic, and if this guy goes above the critical value, this means we have to stop. This means we detected a change point. Okay? So this is a good situation. In the homogeneous situation, all the test statistics are below critical values, therefore we have to select the largest interval.
Now we're on demo.
Now you see how it runs. So these test statistics are recomputed.
Occasionally, a test
We
statistic.
have no jump, so it's okay.
Yes, but occasionally we will observe that a test statistic shoots above the critical values.
What's the true process of Gaussian NCQ?
It is Gaussian space in this case. Now I will introduce a jump again. Say 4. And we see that the test statistics explode immediately. And so
What's the noise, sigma?
1.
Okay, so then the jump is unrealistic.
The jump is larger.
It's very realistic.
Unrealistic.
Very
Okay,
realistic.
come on.
It's exactly what we observed in the
Now
book.
go down, jump just to 1.5, please.
Yeah,
If I can, maybe I can only jump to, I can only jump to
No,
2.
2 is also okay.
So from 4 we jump
From
to
0
3, I
to 2,
suppose.
yeah?
And now where is the 4?
Oh yeah, okay, 4 to 3, yeah.
From 4 to 3. So we see that it was detected. And we see that the statistics that are larger than the critical values gradually move to the left. So
No, maybe just to comment,
itself.
it's very interesting to observe. So I mean, so what you see here, the jump is at this location, which is moving now to the history. And so all the test statistics before are below critical values. And here is the first time when there is a change point inside of the interval, and this is the test statistic immediately explodes. And this is moving in the history, and this is the last interval where everything fine, and this will be accepted exactly. And this is the corresponding length of the interval, and then we see the corresponding estimate.
What about heavier tail distributions?
I only tried this with the distributions from the exponential family.
Of course, I know.
It looks actually similar.
The theory covers that. Yeah, sure, that's what I said yesterday.
Actually, we have simulations, but not in this demo form for heavy tail.
So I can show another jump, but basically that's what I want to show. And I have also a couple of images, again showing the influence of R and alphas on the critical values. So I wanted to jump.
So, has anybody any suggestion which kind of jump? So we can.
This was again a large jump.
Yeah, it's jump to 4.
Jump from 3 to 1, I guess.
Minus 1.
Here we see again the
Minus one
characteristics
is-
staircase. Greater growth of the interval length.
Squared minus 1 is 1.
So can we play also with the other parameters? So here we are varying omega.
Yeah, but we have to restart the program and recalculate the critical values. We took about 2 minutes.
And what happens if the size of the constant approximation is very small? So if we jump up, down,
Yeah.
down.
You can do it step by step and do steps. So, so we can model everything because we run this step by step. We can run this step by step, and so you see. So it's and then you can do jumps. So then the true function.
And then shift.
So now we do steps and so on.
Let's suppose you have a smooth alternative, so it just goes out smoothly, not in a.
No, this demo program only can model jumps.
Yeah, I know. But of course, this theory covers also this situation.
Yeah.
Even with the LCP, it will detect it at some point, right?
If it's smoothly going, then
No, you see, so the estimate goes smoothly at the beginning, from one jump to another.
Yeah, that's clear. That's
but if you have some smoothness in the parameters, we can approximate in a very small jump.
Do you know what the smoothing parameter is in here? It's alpha, the conservative level. That's the smoothing parameter. The hidden smoothing parameter on second level somewhere is deep back out.
It's not the smoothing parameter, right?
Of course, you cannot. But
It's a test is the level of the test.
yeah.
It's the level of the test. So nobody, so this is stupid. So I mean, if people doing hypothesis testing, nobody asks why you take alpha equal to 5%. And nobody object you that you have alpha as a smoothing parameter. It's clear, should be alpha, it can be selected universally for all hypothesis testing problems. Here we have the same situation because our estimation procedure is multiple testing procedure. We have parameter alpha, but now everybody asks us each time why you select alpha equal to 0.5.
Because it's not written here. If you would write it down, then you wouldn't have to ask.
Okay, now we see, I think so everybody can play with this.
Yeah. Okay, now change alpha. I would like to see.
No, we show the result how critical values depend on alpha.
Okay.
Is that very complex?
So now we have a screen this time for the Poisson model, but it is all the same actually. The influence of the parameters is the same for all models. The Poisson model, the critical values for the Poisson model depend on the true value. It is in this case 15. So it was a standard value, and on this picture I have presented the critical values for several true values, 8, 1, 5 and so on. And you see that the critical value actually differ, but again not very much, as was the case with the local model selection and the moving model. Now we come to the case with alphas, and
This is your question. What happens if we
No,
choose
my
alpha?
question was the simulation, how the simulation changed this alpha.
Okay.
it was
I
Yeah.
just wanted, I mean, it's obvious that alpha determines the conservativeness, right? So the critical values. And so for small alphas, you said it's more conservative, yeah?
Yes.
That means for small alphas, the jump detection delay, right, will be larger.
The label is larger.
Exactly, and this is because we think in terms of delay. Of our paper was changing cupola, if you remember, because this is what practitioners ask.
Exactly.
Yeah, and so this is missing in this simulation, that you can change alpha as well.
I will add it in the near future. It is possible. The only problem is the
And it's a smoothing parameter because it will, for small alpha, it will take a long time until it finds it, and for large alpha, it makes tup, but it gets also otherwise very
Yes.
nervous.
What you saw
And that's
was-
what I mean with smoothing
Well-
parameter. It sort of is very keen on doing this for large alpha.
No, what you saw, it was small alpha.
Yeah,
It was not so long.
That was behind his question.
But it was not so long. So even with small alpha, we are quite sensitive.
Yes, very good.
Because the procedure automatically is very sensitive. Okay, so
That was
some.
this last picture with ours, with the powers of
No,
R.
again the same.
It is the same
What
situation.
is the question is, what is the relationship between R and alpha? Can I sort of counterbalance them? Because both are conservative.
Our suggestion, don't put,
sensitivity, and they are sensitivity parameters, second order sensitivity parameters.
our suggestion is not play with R, only play with alpha.
You can suggest that, but it's a parameter that you can play with. So if you want to sell this procedure, somebody asks you how
Hidden R and play with alpha.
hide R and play with alpha.
Now I suggest so you run the procedure for another alpha.
No, but you have to calculate.
Okay. Which alpha you would like to see?
Which alpha I would like to see one.
For which procedure? For
LCP.
It will take a little bit to compute the critical value, but you will get some impression about how long it takes. It's not a very high performance procedure.
Why don't you have this in a database?
Actually, I do.
Yeah.
But from
You
that
just
time,
recompute it to.
So you see, critical value are computed. This is the speed of computing the question.
Why do you call it CB like consolidation?
Critical value.
I see.
No, professionals call it crit V or crit val.
No, what you see here with big
See, that's what
alpha,
I mean. This nervosity, right?
yeah, nervosity increased in the homogeneous situation. Exactly what happened.
But that's what I expected. Yes, that's why you have showed it for small alpha.
Optically, you are right. Optically, it's more clever to show a small alpha. So I mean, if you look at the
And now the
estimate,
delay times will be much shorter.
yeah, exactly. But so this is what you see. This is a payment for
Yeah, sure.
a small alpha. Sometimes you are too sensitive. You react at some fluctuation in the data. It's not big.
Now make a go to one. with the step jump function. Jump to 1, please. Now it should make it.
Well, it should be, yeah.
Yeah, so this should be a much steeper ascent.
Yeah, it is.
Great, good work.
Good, so I think so this is all we want to present. And so